Hi everybody, I'm Mark Weitzman. Welcome back to my playlist on group theory and physics. Today we're going to have our second lesson, and it's going to be basically on low order or small groups and Lagrange's theorem. And along the way I'll introduce some terminology and some other stuff. I already used one word. I think I defined it last time. Let's order. This is the number of elements in a finite group. And let's just quickly review the definition of a group that I gave at the end of lesson 1. A group is a set G with a binary operation Usually we don't show the binary operation. So I'll use star for it right here, but I'll stop using it right away. And it goes from it goes from G cross G into G. So it has to satisfy 4 properties. The first one is closure. So like A star, I'm not going to use the mathematical notation that I used last time, but A star B is an element of G. It has to satisfy identity. So it is an element E such that E asterisk A equal A asterisk E equal A for all A in G. And there has to be an inverse so that for any element, for all A in G, there exists a unique B actually, such that AB equal BA equal E, and then we have to establish associativity. Namely that A, B, C is equal to A, B, C for all A, B, C, and G. And as I mentioned last time, especially in today's lesson, I'm going to start out using what's called tables to represent our groups and to show the multiplication or the star operation. But very rarely do people check associativity. Now, certain things we know will be associative, like if we can represent things as function composition. We know that f of g of, like, we have f of g of x, and we have h of that. And we would use this like as a notation. We would have f composite g and h composite f composite g applied to x. We know sort of by definition this is the same thing as h composite f composite g applied to x. So if we're using certain functions or various things like that, we know associativity would hold. But in general, for an abstract group, just because we write a table and let's say we satisfy the rearrangement lemma that every row and every column contains all the elements of the groups, that's not enough. We still have to show associativity, but associativity is hard to show. Basically, you have to do it, you just have to go through each possibility and show it or find a way to prove it. So oftentimes associativity is the thing that's not checked explicitly. It's just assumed, and someone has checked it. And for certain objects in mathematics, especially in theoretical physics, the octonions have gotten a real lot of play recently. And there's people who spend all their career studying the octonions. So they're non-associative Lie algebras. Anyway, so I want to start. The main reference for today is Ramon's book at the very beginning. He discusses group theory as physicists' first survey. He discusses low order groups, I think up to order 13. I'm not going to go that high. I'm probably going to stop at 6. But I just want to go through the low level groups, and these are things you might encounter. They have some use in physics. So let's start with groups of order. Ramon doesn't even include this group, but technically it's a group, the group of order 1, just consisting of the identity element. Let's just say E times E equal E, E inverse equal E, everything is just E. So this is a trivial group, and the reason why Ramon doesn't discuss it is because it doesn't do anything. If you try and use this for symmetry transformations, there's no symmetry. It's just the identity element. So Ramon starts with groups of order 2, which are important in physics and are often denoted by Z2. And the multiplication table, this is how you show a multiplication table. You put like the group here. Then you list the elements of the group, EA, and then you need to fill in what corresponds. It's like a crossword puzzle. E times E is what? It's E. E times A is what? It's A. A times E is what? A. A times A. Well, okay, there's two possibilities since there's two elements in the group. If AA equals A, we have a problem because then we multiply by A inverse. A inverse A is equal to E. By associativity, this is equal to A inverse A, then times A, which is equal to EA, which is equal to A. So we end up getting E equals A, and we end up having only a one-element group. So this is not possible for a two-element group. And in fact, AA, sorry about that. In fact, AA, which we also sometimes just denote as in regular mathematics, denote by A squared equals E. So this is a two-element group. It's a two-element discrete group. Its importance lies in the fact that it can be used to represent parity, charge conjugation, so anything where when you do it twice, you go back to yourself. You can represent as a group by this thing. And the symmetry transformation, as we know, let's just take the parity example. We know that, for instance, every function we can always represent it as f of x is equal to 1/2 f of x plus f of minus x plus 1/2 f of x minus f of minus x. Now it's easy to see that this is a symmetric function. And this is an anti-symmetric function. So as trivial as this seems algebraically, it's sort of interesting. It says that any function that we have, any scalar function, we can represent it in terms of a symmetric function or an anti-symmetric function. In a sense, we've split our functions into two groups. And this is what group theory does. It sort of finds the representations when we have more complex objects instead of just a single function, but we have, let's say, vectors and spinors and matrices and other objects. We can represent them in terms of different under different group symmetries. So for the group Z2, we only have one symmetry. It's either symmetric or it's anti-symmetric. So we'll get back, in future lessons talking about group representations and the importance of this decomposition here, which is like trivial in this case, but when you get more objects, it's not as trivial. So that's all I can say right now about Z2. Now, the rearrangement, let's go to groups of order 3. And there's only one group of order 3. By the way, when I use this table, frequently people will leave out this column and this row because basically we know what the elements are just from the first row. This is always going to be identical to that, and this is always going to be identical to that. So it's sort of wasting a little space, but I'll keep it that way for now. So let's talk about Z3. So here we'll have 3 elements. Let's call them E, A, B. Sorry about that. Okay, so we can always fill out the first row and the first column because of the properties of the identity. Now, when we go to the other rows, the only thing we know right away is we know that, like this column, this has got to be B and E because of the rearrangement lemma which we established last time, and so on and so forth. Now, it's not hard to show, and I'll sort of leave it as, I don't know what happened there. That this is the only possibility. And this is called the Z3. It's the cyclic group on 3 elements. And essentially, you basically have E, A, and B is actually, if you look at A squared, is B. BA squared. And this is an abelian group. It's commutative. And you just multiply, E, and you multiply by A, you get A. You multiply by A again, you get A squared. And when you multiply by A again, you get A cubed. And it's easy to show that A cubed is equal to E. As a matter of fact, whenever we have a to the n is equal to E, and n is the smallest integer with this property, such that this holds, we call n the order of A. So the order of an element is the smallest integer n such that a to the n is equal to e. How do we know that there is an n? Well, what you do is you start with a list. You start with like a, then you go a squared, a cubed. This is for a finite group. And you assume that, let's say these are all distinct, but if there's like n elements in the, let's say there's m elements in the group, you know, when we get to like, let's start with e here. When we get to the mth element, you know, we have m plus 1 elements here, so 2 of these have to be the same. So we have to have like a to the I is equal to a to the j for I is less than j. And then you can just keep multiplying by, you know, the inverse of a. Let's say the inverse of a is b. Say ab is equal to e. We know every element has an inverse. So I just keep multiplying this by b, you know, I times a to the I. And here I'm going to get, you know, b, I times. I could factor out a, I times, and then I'm left with a to the j minus I. These all cancel, and this ends up all canceling to the e. So we're going to get a to the j minus I equals e. So it's fairly obvious, but it's good to work through this. So that's the order of an element, and we'll prove shortly. We'll prove Lagrange's theorem, which says basically that the order of any element in a group divides the number of elements in the group. So that's not a completely obvious statement, but it happens to be true. So for 3 elements, there's only one group. It's the cyclic group of order 3, and it's abelian. Now let's do order 4. Let me also define another terminology, a subgroup. A subgroup is just what you'd expect. It's a subset of the group. Let's say G is a group. We take a subset, a proper subset of G. And if that subset satisfies all the group axioms, then it's a subgroup. Now every group, like every group G, will have G as a subgroup, obviously. These are the improper subgroups. And we'll also have E as a subgroup. It may or may not have other subgroups. Most groups do have other subgroups, but not all. And I'll show you. For instance, Z3 doesn't have any subgroups, nor does any proper subgroups. They all have G and E, but Z3 doesn't have any proper subgroups, and neither does Z2. So, but most groups do have, most finite groups do have subgroups, and we'll talk about that. Now, order 4 happens to be the first number of elements in the group where there are actually 2 groups. There are 2 groups of order 4. The first group is what's called Z4. It's the cyclic group of order 4. Now, by now you may realize that for every integer n, there's a cyclic group of order n. And so this is just E, A squared, A cubed. Those are the elements of the group. And then by definition, A to the 4th is equal to E. So this is a cyclic group, but there's another group of order 4, which there's another group of order 4, which is actually called the dihedral group, the second of order 2. Anyway, let me put the elements, E, A, B, C, E, A, B, C, I'm just going to fill it in. Now, to arrive at these results, what you can do is first of all, you have to make sure the rearrangement limit is satisfied. And then you can just sort of use trial and error. And if you put in the wrong thing, you'll either get the other group here, the cyclic group of order 4, or you'll get a contradiction. I don't want to go through all the contradictions. But the first thing you ask with this group is, how do you know it's different than the cyclic group? Well, this group has 3 elements of order 2. Namely, you can see that a squared equal e, b squared equal e, just along the diagonals, all e, and c squared is equal to e. Whereas the cyclic group of order 4 has only 2 elements of order 2. Namely, well, a squared, maybe it has 1 element of order 2. I'm sorry. Yeah, because I don't think I consider e as being an element of order. E is an element of order 1 because e to the 1 equals e. So let me just erase that. So there's 1 element of order 2, namely a squared is equal to e, because a to the 4th is equal to e. If we were to take a cubed and square it, we'd get a to the 6th, and we'd see that that ends up being equal to a squared, which is not e. A happens to be equal to a squared when we square it, and it's not equal to e. So there's only 1 element of order 2 in this group, and there's 3 elements of order 2 in the dihedral group. So this group is also called, it's a famous group, it's abelian, and it's sometimes denoted by V, and it's sometimes called Klein's 4 group. Anyway, nothing deep here, but at least we've shown that we can have different groups that are not isomorphic of the same order. And I don't want to get much into abstract algebra in this course, but you always have to check that when you have 2 different groups, when you label these, sometimes if you relabel some of the elements, you get the same groups. And that would be called an isomorphism, or even an automorphism sometimes. So you don't have to, just because you have several different tables, they might all be the same when you rename the elements. Okay. I want to go on to the dihedral group. I should explain more what it means, but in the case of D2, it really concerns a geometric figure of 2 points. And basically the symmetry of 2 points, imagine this is a plane, you can either reflect about this axis, or you can rotate by pi. So that's 2 symmetries in this group, reflection and rotation. It's pretty trivial for this group, but when we get to D6, and this is often, we denote these by like the number of elements times 2. When we get to the next dihedral group, you'll see that it's less trivial. Let's go on to order 5. Now there's only 1 group of order 5, and that's Z5, the cyclic group of order 5. So how do we see this? Well, here, we'll prove it in a minute or two, but here we use Lagrange's theorem. The order of the element has to divide 5. So that means it could either be an element of order 1, and there's only one element of order 1, because that means a to the 1 equals e. So this is just a. So there's one element of order 1 in every group. That's the identity element. And then all the other elements would have to be of order 5. So we have to have a to the 5 equals e. And so our group then becomes 1, comma, a squared, a cubed, a to the 4th. So this is going to be a general rule that when the order of the group is prime, there's only one group, ZP. If order of group is prime, then there's only one group. Of that order, namely ZP, cyclic group of order P. Okay. Now, before proving Lagrange's theorem, I want to by the way, this group of order 4, I left this out, this has subgroups. For instance, let's look at the Klein 4 group. E comma A, let's see if that's a subgroup. Well, E is always going to be in the group, and then EA is A, that's in the group, and A times A is E. So this is a subgroup, and E comma B is a different subgroup, and E comma C is a subgroup. And we'll also show, it also follows from Lagrange theorems, that the number of elements in the subgroup has to divide the order of the group. So here we have a 4-element group. The only divisors are either 1 and 4. Those are the improper groups, subgroups, namely the whole group or the identity group. But 2 also divides 4. So there is can be subgroups of order 2. And the same thing here, the only subgroup is E comma A squared. I should be using sets, but somehow some people use parentheses. So this is a subgroup as well, because A to the 4th is equal to E. So there's only one subgroup in the cyclic group, but there's 3 in the Klein group. And one more thing I want to go over is direct product of groups. This is a very simple construction. If we have like 2 groups, G1 and G2, these are completely separate groups. They don't have any elements in common or anything. They act on different spaces and everything. So we consider the direct product group is equal to the set of all ordered pairs. Now I'm using the real ordered pair notation here. Of all ordered pairs, so that G1 is in G1, small g1 is in large G1, and small g2 is in large G2. And how do we define multiplication in this group? Well, G1 comma G2, that's just the very natural multiplication that you would expect. I'll even put the star there. H1 comma H2 is equal to G1 H1 comma G2 H2. I did that wrong. No, yeah, I did it right. G1 H1 G2 H2. So This is a useful way of getting other groups. If we have two groups, we can just take a direct product and we get another group. And that's one way. If we take Z2 cross Z2, you'll find that we get the D2 or V that we talked about earlier. Now, let me do the group of order 6. I should say groups of order 6. So as usual, there's a cyclic group. But then there's another group, which is called D3. And it also has another name, S3. And I'll explain that in a second. This is the last multiplication, as Ramon says in his book, this is the last multiplication table he's doing because they get pretty big. And I'm just going to use subscripts now to label the elements. And then it's not easy in this multiplication table to see the pattern, and I'll give a much better way to see what's going on here, but I just want to write this down for reference. So what's involved here is first of all, this is our first non-abelian group. So let's check that out. So if we do like A1, A3, it's equal to A4. A1, A3 equal to A4. But A3, A1 is A5. So that tells you already something. Now, I want to explain the names, the dihedral group. The easiest way to see this is think of the symmetries of an equilateral triangle. And so imagine here's A1, here's A2, and here's A3. So there's altogether 6 symmetries. The first one we can do nothing. I'll call that E. The next one we can rotate. This is the center of the equilateral triangle. We can rotate the trial counterclockwise by 120 degrees. So in that case, I'll just put rotation pi 2 pi over 3. We can rotate it by 240 degrees. Notice when we do, if I were to do this rotation, I would have an equilateral triangle. Now A1 would be here, A2 would be here, and A3 would be here. I could do a rotation by 4 pi over 3, in which case I would get A3 here, A1 here, A2 here. And if I do another rotation, I get back to where I started, so that's not going to do anything. But now I can also do reflections. And I can reflect about this perpendicular bisector. That's supposed to be perpendicular there. And I can reflect about this perpendicular bisector. And I can reflect about this perpendicular bisector. So if I call the sorry, there's no So if I call these reflections little r, I can reflect about A1, and then that would give me a triangle. A1 stays the same, but this becomes A3 and this becomes A2. Or I can reflect about A2. That gives me a triangle where A2 stays the same. This becomes A1 and this becomes A3. Or I can reflect about A3. And then I have A2, A1, and A3. So these are the 6 elements of the group. And notice that it's easy to see that the elements are R2 pi over 3 and R4 pi over 3. They have order 3. So if I rotate by 120 and then another 120, then another 120, I get back to where I started. If I rotate by 240 and then I rotate by another 240, I get 480, and then I rotate by another 240, I get 720, and I get back to where I started. Whereas the reflections, RA, RA1, RA2, RA3, have order 2. And you can see that there are subgroups. So we have subgroups, lots of subgroups. RA1 is a subgroup. RA2 is a subgroup. And RA3 is a subgroup. We also have a subgroup R2 pi over 3, R4 pi over 3. Notice that the number of elements in each subgroup in case of the reflections is 2, which divides 6. In the case of the rotations is 3, which divides 6 as well. So you can start to see that this is sort of an interesting group. And we call it the dihedral group because it's got these two symmetries. When the number of sides of the regular polygon is odd, we have the rotations all the way through, n minus 1 rotations if it has n sides. And then we have the reflections to the perpendicular bisectors. When we have like a dihedral group of the square, now we get 3 rotations as before. I mean, I can rotate that there, then rotate it there, and rotate it there. So we get our rotations, which are 3 of them. We also get reflections here. So these are like the reflections we had in the triangle group. We get 2 of them now. But we also get reflections about the diagonal. So we'll have like an 8-element group. And there are several groups of 8 elements, and I don't want to cover them all. There's a quaternion group of 8 elements also. But in this case, this is the dihedral group of 8 elements, which is D4, and it consists of the identity, rotation of pi over 2, rotation of pi, rotation of 3 pi over 2, and then a reflection about the corners. Well, there's going to be 2 reflections which are about the bisectors. Let's call them B1 and B2. And there's going to be 2 reflections about the diagonals. Let's call them D1 and D2. 1, 2, 3, 4, 5, 6, 7, 8. So this is, and if for every n there's a dihedral group of 2n. Now, I also called this, as you might notice, I went back and I called it S3. S3 is the permutation group. on 3 elements. And in general, we'll talk about it next time, but Sn has n factorial group elements. So you can see 3 factorial is 6. And it just permutes the elements of the group. If you go back to these triangles, you can see that what I'm doing is I'm sort of doing, I can sort of say I'm A1, A2, A3 is going to A2, A3, A1, and so on. All of these things will have a permutation associated with them. And for those who know something about permutation groups, for 3 elements, there's 2 cycle transformations corresponding to the rotations. I'll talk about that in the next lesson. And 3 transpositions corresponding to the reflections. So in the case of 3 only, S3 is isomorphic to D3. But for general n, as you can see just by the number of elements, Sn is, not isomorphic to a Dn. Sn has many more elements. Okay, so I covered there that I don't want to go beyond 6. 7 is obviously the cyclic group. 8, I believe there's 5 groups. I mentioned the dihedral group and the cyclic group. There's also the quaternion group. I think there's 2 other groups. I'll check that in a second. But let's just prove Lagrange's theorem. Which is that I'll prove it in the sense that the order of a subgroup divides the order of the group. So let's say we have a group G with n elements. We have a subgroup H with m elements. So let's just list the group H. So H is going to be equal to E. Let's call it G1, G2, all the way up to GM minus 1. Okay, that's H. Now what we do is we take any element that's in G. This is a proper subgroup. Let's call this a proper subgroup. I mean, it's trivial. If H is an improper subgroup, it's either has n elements, in which case that divides the order of G, or it has 1 element, and that divides the order of G. So let's just do the case of a proper subgroup. So that means, since there's m elements here, there are elements in G that are not in H. So choose, you know what, I mislabeled that. Let's call this H1, H2, Hm minus 1. So choose an element G1 not in H. Okay. And now form the group. In abstract algebra, this would be called, I always get confused whether it's a left coset or a right coset, but it's a coset. Let's form the set G1H, and this is equal to, we're going to multiply G1 by every element in H. G1E, G1 H1, G2, I'm sorry, G1, H2, G1, Hm minus 1. Okay? Now, claim, my first claim, every element in G1H is distinct. Okay? Is distinct from any element. Well, they're all distinct from any element in H. They're all distinct in terms of themselves because we can't have, like, if we had G1 H1 is equal to G1 H5, we could cancel the G1s, just multiply by the inverse. With group theory, you can always cancel because there's no zero elements. And we would get H1 equal H5. But these are all distinct elements of H. So all of these are distinct. There's M of them. They're all distinct. And none of these is equal to any element in H. So let's prove that. So if we were to have something like let's say H6 is equal to G1 H4, let's say we had something like that, then we could multiply by H4 inverse on the right. We get H6 H4 inverse is equal to G1. Right? Because H4 inverse cancels that. But H6 is in the subgroup H. H4 inverse, to be a subgroup, every element inverse has to be in that group as well. These are both in H. So their product is in H. And this implies that G1 is in H, but that contradicts. That contradicts when I said choose G1 not in H. So what have we done? We found another set which has M elements. So the set H has M elements. G1H has M elements. And if we haven't exhausted the group G, we can choose another element, call it G2, which is not in either of these sets. Say G2, not in H, not in G1H. And then G2H, by the same argument, will have M elements. Well, eventually, since it's a finite group, we run out of elements, and basically what we've done is we've partitioned G into subsets of M elements. So M has to divide, that's the symbol in number theory, has to divide N, and that proves our theorem, QED. Okay. So that's all I want to say right now about the low order groups and everything. I do want to show you something. This is from Ramon's book. Didn't come out that great. Let me see. Well, it doesn't really matter, but you can see the group of order 2, he has one group, cyclic, order 3, cyclic, order 4, 2 groups, cyclic, and Klein's 4 group, order 5, cyclic, order 6, the cyclic group, which is also can be shown to be Z3 cross Z2, direct product, the dihedral and permutation group S3. He has a star here to indicate non-abelian. 7 elements is cyclic. 8 elements, there's 5 different groups. There's a cyclic group. There's a group called Z4 cross Z2, which is abelian. There's a group called Z2 cross Z2 cross Z2, which is dihedral group cross Z2. Then there's D4, which is dihedral group, which I mentioned earlier. This is non-abelian. And then there's another non-abelian group called Q, or Q4, which is quaternionic. They sometimes call it dicyclic. Anyway, this goes on. I cut that off, but the interesting group is this T, this tetrahedral group, is what's called A4, the alternating group, which is all even permutations of 4 elements. Notice I said even. So this has 12 elements because S4 has 24 elements, and if we take the even permutations, we have 12. So this is the symmetry of the tetrahedrons. And just to add one thing, I won't define what a simple group is, but for those who know what a simple group is, A5 is the first group that's simple. A5, first simple group, has order 60 because it's the S5 has 5 factorial equal 120 elements, and this is just even permutations. And the great thing about A5 is that because A5 is simple, and what simple means is that it has no invariant subgroups. It does have subgroups, but it doesn't have invariant subgroups. And I don't want to define right now what an invariant subgroup is. But this implies, and this is what's great about group theory, this implies that there's no general formula for solving 5th degree algebraic equations. So it turns out that, A4, A3, and A2 are not simple. Well, A2 may be simple. Let me leave that. So this has 12 elements, and this has 3 elements. So we can solve 4th degree and 3rd degree equations, and you may know those formulas, but we can't solve a 5th degree equation. So I'll stop right here, and for the next lesson we'll go on to permutation groups. Thank you very much for watching.